All right, so welcome. This is lecture 16, part 3. We have a part 3 that I didn't anticipate, but on Quadrature Amplitude Modulation and Reception, receiver design. This is the real-time digital signal processing lab at the University of Texas at Austin for the spring 2014 semester. So last time, we went through almost everything and got to the adaptive equalizer, and we stopped there. So I'll go back to the adaptive equalizer, and then we'll finish up with Quadrature Amplitude Demodulation. So in part 1, we did introduction and automatic gain control. Part 2, we did carrier detection, symbol clock recovery, and some of the issues in channel equalization. Now we'll do the adaptive equalizer, which is homework 7 due next lecture. Let's move on to, so we left off right here on 16-9. So let's go back to it just to set the stage for the adaptive equalizer. So what we have physically is transmitter, channel, and receiver. So what we physically have is along this path. All right, and that is our signal path. And the job of the equalizer, as we talked about in part 2, is to compensate for distortion, frequency distortion in the channel. And in practice, this channel is going to vary in time. So the channel model I have shown here is an LTI filter plus noise. Now, in practice, this LTI, the coefficients of my LTI filter will vary with time. And then I have noise. Okay. And of course, the noise is random. You know, it's going to move around. What we like to have is an equalizer that can track the changes in the channel as it's being trained, as it's learning about the channel. What we like to have is after the training, so we're going to send some training data over the channel, which I asked last time, is, and you said it was pseudo noise, which is correct. So typically, this is a training sequence is a pseudo noise sequence. So typically pseudo noise, but not exclusively, but something that we can easily regenerate at the receiver. Okay, so typically pseudo noise. So pseudo noise sequence, lab 4 for this class. And the equalizer's job is, again, going to try to create the right FIR filter to undo the magnitude and phase distortion in the channel. Now, this is not just a communication system application. You can equalize anything. Anything. Speakers, microphones, biomedical test equipment, it doesn't matter. As long as you have the ability to train, to send some known calibration signal and then adapt an equalizer or train an equalizer to compensate for whatever the impairments are. This is an incredibly effective method. And this method we'll do today works in any application. It's not specific to communication systems. Now, there are equalizer designs that are specific to communication systems or tailored, but the one we're going to do is not. And the one we did in part 2 for infinite impulse response equalizer also is not tied to communication systems. So our goal is to have, again, an equalized channel, which means the cascade of the channel and equalizer look like an ideal channel. And the ideal channel that we're going to talk, for this case, is a delay followed by a gain. And it's very easy to reverse this or do the undo operation here, and that is to say scale by 1 over g and throw out the first delta samples. And we've undone the cascade of the delay and the gain. Now, the ideal channel doesn't physically exist, and so I've drawn this dotted line here to show that this ideal channel is what we'd love to have. It's not what we actually have. So in doing equalization, what we're going to compute is an error between what we have, which is the signal path in blue, this blue arrow. All right, so again, here's our signal path in blue. So the error is the difference between what we have and what we like to have. Okay, so what we have again is this blue arrow signal path, and what we have is a signal path, the blue arrow. We'd like to have from input to the error signal. So the input to the output of the ideal channel is we'd love to have the output of this ideal channel to be exactly the same as Rm. So we'd love to have this S sub m to be the same as R sub m, and if we do that, the error is 0. So our job in designing an equalizer is to drive this error to 0. Go ahead. That delay is a parameter. This delta is a delay. It corresponds to the delay through the channel and through the equalizer. So this delta includes the transmission delay through the channel and the delay through the equalizer. Now, this equalizer will not be linear phase, so in reality, our delay will be frequency dependent. So this is like you might consider an average delay through the channel and the equalizer. We have to search for it. So either we just fix delta and do the best we can, or we search for delta, which is what's on homework. So in practice, if we have the computational resources, and we do this in DSL, for example, we search over a range of delta, and we know what that range is from field studies. We know that it's not, 300 possible values. It's a very narrow, in DSL, it could take on any value, I suppose, up to a couple hundred, but we know that it resides in a very small window of about 10 values. And so we need to search over those 10 values and just pick the best one. In homework, what you're going to look at is let the delta, this delay, be no larger than the worst case delay through the equalizer, which is the equalizer length minus 1. So in homework, we're going to set the equalizer length and then search over all possible delays, get the best equalizer, increase the equalizer length by 1, search over all delays, get the best equalizer, and we're just going to eventually find an equalizer that will drive this error to the smallest value. So we also have to limit how long the equalizer can be. So we have to set an upper limit on that. I think I tell you 40 or something in the homework ends. Get what I wrote. Go ahead. Correct. Right. So S of m is the output of the ideal channel, which doesn't have noise. Right. So the ideal channel is just delay and gain, but the actual channel, the channel model we're using up here is LTI system plus noise, but in reality, that channel can be even uglier than that. Correct. We're also going to try to clean up some noise on this one. So the nice thing with this equalizer method is it will track, the adaptive method on the next slide, will track changes in the channel over time, including variations in the noise. Correct. So the input's the same in both cases. So in the signal path, it's the actual transmitter. It's the actual transmitter that transmits this training sequence. In practice, it'll be pulse-shaped and all that. But here I'm just showing you, for the purpose of the homework and for these slides, X of m is just symbol amplitudes coming at us. Or it could be samples, I suppose, PN samples, since m is the sampling rate. So this is just samples coming at us at the sampling rate, not the symbol rate. So this equalizer, runs at the sampling rate of the receiver, and we're going to update it at the rate of the sampling rate of the receiver. So we're going to update it every time a new sample is received. We're going to be updating the equalizer coefficients. That's on the next slide. That's homework problem 7.2 is the adaptive equalizer. All right, so let's go ahead and, okay, so and then on the receiver, it's going to generate the same, because it knows what PN sequence the transmitter is using. So it's going to regenerate it in the receiver. And how do I know to line up? So I have to synchronize in time here. So how do I line up the time axis, the time sampling time? What do I do? Autocorrelation, but more so correlation. So I know what I should be receiving, and so I can kind of line up. And the delay can also take care of it if I let the delay be long enough. But I can correlate at the receiver at the input to the receiver, I can correlate against the PN sequence that I'm looking for to find out what the delay is. I look for the peak. So that's one way that I can line up, I can get the M's. So if I were to do that, I would insert a delay before the equalizer just to line up and synchronize the sampling time. Okay. Or I can just let delta deal with it. I can let delta handle that slack if I let delta be large enough. I just let it take care of it. Either way. So again, delta includes the delay through the channel and the equalizer in the ideal channel model. Now, we don't know what G is in advance, so in homework, I've asked you simply, this is an unknown, right? So G is unknown. But there are ways we can get at G, and in homework I said just set G to 1. All right. What this also means is that we can do, we can again we can throw automatic gain control in this, and we're fine. So the point is that we can handle any gain in the ideal channel. So we can set it to be a constant and be done with it, or there's certain ways we can get an estimate of what G is. But for now, we'll just let G be 1, and we're good. All right, so let's derive the adaptive equalizer for the simplest case, which is an equalizer that's an FIR filter. Hey, Andy, I think we're getting some bleed through on the speakers.
I'm sorry?
I think we're getting some bleed through from the speakers from another room.
Okay, I just turned off the room volume. Let me know if it goes away.
All right, thank you. So the simplest case is a 2-tap equalizer, and we're going to let the first tap be fixed at 1. So the first tap, so it's 2-tap, right, 2 real value coefficients, and we set the first coefficient to be 1. So in this case, this would be our coefficients are W0 and W1. So W0 here is just fixed to 1. And we're going to let the second tap vary with, we're going to adapt the second tap to find out what's the best value possible. So we'll derive the update equation using what we've been doing for adaptive steepest descent algorithms. Same block diagram as before. So if we look, again, the signal path that we have, so there's our signal path again. So let's start deriving this. So I have an error signal. This is the difference between what I really have based on the current value of the equalizer coefficients, which I'm going to be updating, subtracted from what I'd like to have, which is this S sub m. So that's my error calculation. What is S sub m? Well, S sub m is just the training sequence that I'm generating, delayed by delta samples, and scaled by G. So there that is. Okay. Let's now find out what R of m is. Well, R of m is just the output of the equalizer. Remember, the equalizer is FIR, 2 coefficients. So we know from if this is the impulse response up here for the equalizer. So the input-output relationship is simply the output R of m is simply the input plus W1 times the previous input. Just an FIR filter with 2 taps. And the first tap is equal to 1 in value. Standard stuff. So again, the output is just equal to the current input and plus W1 times the input 1 sample ago. So Y of m is an input. You're probably used to seeing that as an output, but it's an input here into the FIR filter. Okay, so that's R sub m. Now, how do we update the coefficient W sub 1? Well, steepest descent. So I do my update equation. So I have the next value W1 is the current value W1 plus an update. And the update is, now it depends on the cost function I'm going to go after. So I'm already kind of implying here that my cost function is something I want to minimize by having the minus sign there. So I have minus mu, my step size, times the derivative, Right? I'm going to go, in this case, I'm going to descend a bowl. The way I'm going to do the cost function. All right, so I want to take the derivative of some cost function, which would be a least mean squares cost function, with respect to W1. And then replace W1 with W1 of M, which is the current value of that coefficient in the FIR filter, that tap in the equalizer. So a lot of cost functions I can use, the least mean squared is saying, okay, take 1/2 times the error squared. So we're back to descending a bowl, basically, finding the minimum point of a parabola, a bowl, parabola, whatever. Now the half is simply, it just means that when we take the derivative, the derivative that we get from e squared, right, of m, that 2 will multiply out times the 1/2 to give us 1. So the coefficient here doesn't matter because the idea here is to drive this cost function, JLMS of m, to 0. And if we've done that, we've driven the error to 0. So the error can be positive or negative. What we want to do is drive the square of the error to 0. So let's go ahead and work through this. So to take the derivative of the cost function, we also call this the error surface objective function, lots of names for this. Take the derivative with respect to W1. So to kind of work back, so what's E? E is R of M times S of M. S of M does not depend on W1. Does not depend on the equalizer coefficients at all. It's a constant with respect to the equalizer coefficients. R sub M does depend on W1. Okay, so if I differentiate the error function here, I'm going to get the S of M term goes to 0. When I take the derivative with respect to W1, the R of M term, the derivative is, what's the derivative there? Y of M minus 1. Right, so there's my derivative. And then I have to do the chain rule and stuff. So I have 2 times, 1/2 times the error. 2 times 1/2 is 1. And times the derivative of the error. So I get, the error times the derivative of the error with respect to W1. And that's it. It's a very simple equation. Very few mathematical operations. I have 2 multiplications and 1 addition for my update for each coefficient. Extremely efficient. Separately, to compute R of M, which I will need as I go through this, is just running an FIR filter. All right, so because in order to compute E sub M, I need to know what R of M is. So I have to compute it. So I have to run the input Y of M through the filter to get R of M as part of the update. Okay, so there is another multiply add to worry about. So in the end, if you and you'll see this on homework 7.2, it's basically 3 multiplications per coefficient per update. Extremely efficient in operations and takes very little memory. All I have to store, the FIR filter has to store, the current and previous values, right, equal to the length of the filter. And I probably have to make S of M a vector, so it has to be the same length as probably the FIR filter. And there isn't much else. Very little memory here to be used. Because I don't have to store the PN sequence, because the PN sequence I can just generate. Now I could store it if I wanted to, but there's no reason. I can just generate it very easily on the fly. It's a very efficient algorithm. It tracks changes in the channel over time. And you'll see it in the homework. You'll get about the same result in terms of the error function, the objective function that you get. Will drive the error close to 0. It behaves very similar to least squares method, but takes a whole lot less calculations. Orders of magnitude in the homework problem that you were asked to do, least squares will take orders of magnitude, several orders of magnitude less computation, several orders of magnitude less memory to deliver the same result. Okay, so the least squares method is really common in desktop simulation. It's less common in a fielded system. We do use it on occasion if we have a very short training sequence and a very short equalizer. We might use least squares. We do on occasion. But if we have any sort of long equalizer or long training sequence or both, the adaptive method's the way to go. Now, beyond the computational side, the least squares method has another downside, which, again, we don't have the least squares method here in the slides, but in the book, least squares method gives you the average equalizer over the training sequence. It doesn't track the channel over the training sequence. So when the training is done and finished, the training sequence is finished, the least squares equalizer gave you the average case, but it doesn't tell you where the channel is at right now. That average case equalizer may not be very good, given the current channel. Now, in homework, your channel isn't changing with time. In homework problem 7.1 and 7.2. But in practice, the channel is going to change with time, and that's another reason to use the adaptive method. It will track the channel changes over time. Now, again, if the training is really short and the channel is probably not going to change over a short training period, the least squares method is a fine choice, and we do use it in practice. But in my experience, it's more common to use an adaptive FIR channel equalizer in practice. But both have their place. Go ahead. This is fine. This will track it. Because remember, the adaptive method only looks at the current time and the past window of, as many samples as the FIR filter has coefficients. So it only updates over recent memory. It doesn't remember what happened a long time ago in the training sequence. And that's huge. That's why it tracks the channel with time. If you're and there are certain channels that change like crazy versus sampling rate. Underwater channels are an example of this. In DSL, we do it this way. In high-speed mobile, do it this way. Well, it depends on the length of your training sequence in the mobile case, but we would generally want the adaptive way to go. And again, this is not, there's nothing in here that talks about modulation type, method. There's nothing communication system here. It's just training sequence, which PN or whatever, an unknown channel or unknown media between transmitter and receiver. It's not for anything, audio, biomedical. We use this in image processing, video processing. It's a very generic method here for equalization, with the goal of having the cascade of the channel and the equalizer being close to all pass. That's the goal. The equalizer is supposed to undo the frequency distortion in the channel. So the equalizer here can handle linear, time-varying effects. The adaptive version. It's huge. And it works fine in the presence of noise. Least squares equalizer has another problem in that it can amplify noise if you're not careful. Depends how you do the least squares equalization. Now, also in this method, you'll notice that we didn't have to estimate the channel impulse response. We don't need to do that. It saves us a little bit of trouble as well. We don't need to know the coefficients here, the FIR coefficients for the channel model. We don't need that information. We don't care for the equalizer. We may need it for other reasons in the receiver at other times, but for the equalizer, for this method, we just don't need it. We just go simply off of received values y of m and a known training sequence, and we're good to go. Pretty cool stuff.
So you keep making your equalizer longer until you have
Lots of ways you can do this. So in practice, the equalizer is could grow during training, because you can do whatever you want during training. So you can search for. So you can look at, okay, I'll look at, in practice I might look at 2 or 3 different lengths and pick the best one. Or a standard might give you some insight how long that equalizer should be. And it's a matter of searching. Remember, we got 2 free parameters here at least to search over. One is the FIR the length of the FIR equalizer, and the other one is the delta. So we have two different values to set. So so in the DSL case, we tend to set the equalizer length and search over a small range for delta to find the best one. But there are other cases where we might pick 3 or 4 different equalizer lengths and just see which one gives us the best, the smaller error surface. Now, in homework 7.1 and 7.2, I asked you to also look at bit errors. So there we are now interpreting, so beyond the usual objective function, some sort of least squares objective function, in the homework I also asked you to look at bit errors. So we are going to use this in the context of a communication system, but what I derive here has nothing to do with a communication system. Any other questions? Okay. So we go back quickly to the overall system here in the QAM receiver, way back to part 1, lecture 16. This is the receiver in the bottom half. And again, our signal path is what's shown in blue. And we've gone through the different steps in the we'll talk a lot about AD conversion coming up next week. But we have some ideas what that is from our discussions in class. So we have a bandpass filter, analog bandpass filter to enforce the transmission band, attenuate out-of-band noise and interference. AD conversion, which is going to be filtering, sampling, quantization. Channel equalization, which we just covered. Off to the side, we have symbol clock recovery, automatic gain control, carrier detection, which we've talked about earlier in parts 1 and 2. And this now remains, so if all the adaptive systems here are doing their job, now we can talk about QAM demodulation doing its job. But QAM demodulation depends on all these earlier systems getting it right, at least close to being right. Symbol synchronization, channel equalization, etc. So let's talk about that last step, the baseband QAM demodulation. So our job is to recover the baseband in-phase and quadrature signals. This would be ultimately the amplitudes, the symbol amplitudes that the transmitter was using on the in-phase and quadrature directions for the QAM modulation. This is going to assume perfect automatic gain control, equalization, symbol recovery, etc. So if I'm a little bit off in one of these adaptive systems, I'm going to see more errors at this stage. As before, QAM demodulation is going to consist of QAM modulation followed by low-pass filtering. So the F max that I end up with is going to be, and this is important to set the sampling rate correctly to either reduce aliasing or know where the aliasing is going if you don't quite satisfy the normal Shannon sampling theorem. So the maximum receiver frequency, because we're going to have this modulation stage, is going to be, in hertz at least, 2 times the carrier plus the bandwidth. Because what we saw when we get at the receiver is going to be something at the carrier, and the transmission bandwidth is capital B, so plus or minus B over 2. Right? So at the receiver, we're going to see a bandpass transmission. This is QAM, so this is the QAM carrier frequency, and this width is capital B. Now that width is going to be, so if we upconvert, so if we modulate, make sure I got my definitions right, I get 1 at 2 FC, I get 2 lobes here at 0, or 2 parts of my spectra. So I guess this has to be 2B. And so this upper edge is 2FC plus B. This is going to be, if we did everything continuous time, This is the frequency, this is the max frequency we need right here at the output. And then we low pass filter to pick off the baseband component. If we don't choose the sampling rate to be more than 2f max, which we've seen on homework problems, back to the problem of, where it printed, I wish I were an Oscar Mayer Wiener, that problem. Okay, so that one has got some of the choices there lead to aliasing. But it still can work even with aliasing. All right, so this modulation step in the receiver is going to, increase our max frequency. So when we choose the sampling rate, we have to be aware that we, either we obey the Shannon sampling theorem, or if we don't, we have to know where the aliasing is going to go, where the aliases will go, to make sure they don't interfere with our baseband. Okay, and we talked before, so this low-pass filter after the modulation step here is the demodulating filter. It's going to pick off the baseband component. It also has other roles. I mentioned this before. It's also the match filter. It's also the anti-aliasing filter prior to downsampling by L, the number of samples per symbol. And we already know that the match filter, so we just basically let the low-pass filter be the match filter, matched to the pulse shape used by the transmitter. We already know that this maximizes the signal-to-noise ratio at the downsampler output. We also know from deriving symbol error rate that the symbol error rate is a Q function of the square root of SNR. So if the SNR increases, what happens to the Q function? It drops dramatically, exponentially. So in terms, if I have SNR in linear units, so if I increase the SNR, I have a dramatic decrease in the probability of symbol error. So the match filter is doing what we really what we want it to do. And maximizing SNR is a good thing in general, but depends on the application, how important that really is. For this application, it's exactly what we want to do. Exactly what we want to do. Now, you can also look at this demod in terms of trig formulas. We'll do that here. So again, my baseband signal at the transmitter side is, I don't have, I guess this is without pulse shaping. I have the in phase, and I guess you could use I of M as if you wanted to include the pulse shaping, you can put that in the I of M. So I of M is here going to be our symbol amplitude in the in phase direction. Here's Q of M, which is a symbol amplitude in the quadrature direction for the QAM constellation map. For QAM demodulation, we're going to simply take this baseband signal X of M and multiply it by a cosine, and then low-pass filter to get the in-phase component, and we're going to take X of M multiplied by a sine, low-pass filter to get the quadrature component. So just the math on this, so if I take X of M and I modulate, so I'm going to demodulate, but to demodulate, I'm going to modulate in low-pass filter. So I have to do this gain by 2 to offset the cosine, the effect of the cosine. So anyway, I have 2 X of M cosine omega C of M, omega C times M, and I can just substitute in X of M and multiply through, and so I end up with I of M times the cosine squared, and then Q is times a sine of theta, cosine of theta. And I can use some double angle, I can use some trig formulas here to help me out. So I can use, so here's cosine squared formula, so I can replace the cosine squared term with the DC offset of 1/2 plus times 1 plus cosine of 2 theta. So we see that here. So I get I of M, if I multiply through by I of M, I get I of M times 1 plus I of M times cosine of 2 theta, and theta here is omega C. Oh, that's a mistake. That T got left over from an earlier version of the slide. That should be an M. And then the double angle formula, this formula here also has a trig formula, so we can replace that with the sine of 2 theta. So we're left with the baseband component, I of M, and the second 2 terms here are components that are centered at twice the carrier frequency. Low-pass filter gets rid of those. We're left with baseband. That's the quadrature So that's the in-phase direction. Sorry, the quadrature direction, remember the key here is to multiply by -2 sine. And I've made this mistake many times. Forgot the minus sign. All right, so -2 times sine. And then we're going to follow this modulation step with a low-pass filter to do the demodulation. And again, we have the same procedure, pretty much the same procedure as before, except that now I have a sine squared term. I need that trig formula for the substitution. I have a cosine sine as before. And working through the algebra, I'm left with a baseband component centered at 0, and then another component, or two components, centered at twice the carrier. Apply the low-pass filter, extract the baseband component.
Why do we use minus sign in the modulation?
Because in the so why do we use minus sign here? Because in the transmitter, what happens?
We use minus sign.
We use a minus
Why do we
sign.
use minus sign there?
They have to match. Otherwise, you're out of phase. Go ahead.
So what did cost on
That should work.
that should work as
That should work as well. But there's a reason we do the minus sign is it's a way to implement a frequency shift by e to the j theta, and then we take the real part for transmission. So the minus sign is the right way to go about that. The derivation is not fresh in my mind, but the minus sign is what we want to do. But whatever we do, the receiver just has to do the same thing. Otherwise, what happens? I'm out of phase by 180 degrees if I don't have the minus sign right. It's going to do a mirror image of my constellation, which makes the constellation look the same, but the bit patterns aren't the same on that flip. You get lots of similar errors. That's when you know you missed the sign. When the receiver's just not working for anything. You're as good as randomly guessing. That's when you know something's really wrong. So this is a good place to check. Any questions on this? All right, so that ends lecture 16, part 3.